Everybody knows how to write the stress tensor, but do you know how to draw the stress tensor? In this video, I will show you how to express the stress tensor in diagram form. Not only that, I will also show you how to convert between the matrix form and the diagram form of stress tensor. Watch until the end and you will gain an extraordinary level of visual understanding on stress tensor. Suppose a fluid is flowing within the confined space of two boundaries. The fluid has all three velocity components, Vx, Vy, and Vz. We want to find the forces on an imaginary cube within the fluid. The test cube is arbitrarily chosen, has a finite size, and fixed shape. Because momentum transfer is omnidirectional, force should act on all faces of the cube. The force on each surface can be in any direction. Whatever direction, they can surely be decomposed to three components. To begin our analysis, we need to label the 9 component forces in this diagram first. We shall adopt this set of notation rules to start with. The magnitude of the stress is sigma, with superscript P and subscript Q. Superscript P to indicate the plane on which the force acts. Subscript Q to indicate the direction of the force. Labeling the x-plane, this is what we get. Similarly, we label the stresses on the y-plane and the stresses on the z-plane. The stresses in the x direction are composed of sigma x star, sigma x double star, and sigma x triple star. These three stresses act in the same x direction because they are generated by transfer of the same momentum source, the x momentum. Because the x momentum is transferred to all different directions, it is received by different planes and therefore produces forces on those different planes. The total stress in the x direction is the sum of these three stresses. There are two kinds of stress, shear stress and normal stress. Shear stress acts parallel to the plane. It is produced when momentum is transferred perpendicular to the fluid flow direction. Normal stress acts perpendicular to the plane. It is produced when momentum is transferred parallel with the fluid flow direction. Here is a pop quiz now. What is stress? Many of you would answer, stress is force divided by surface area, which is normalized force. To me, the wording of this question makes it seem a broad sense question, so the expected answer depends on the context you are under. In academic settings, it depends on the subject you are taking. For A-level physics and solid mechanics, the normalized force answer is 100% correct, but in fluid mechanics, this answer is just 50% correct. In fluid mechanics, normalized force is just the acting form of the stress. We have another propagating form of the stress. In fluid, a stress has two forms, the flux form and the force form. Both the flux and the force forms are vector quantities. They have the same magnitude but different directions. The flux form is the propagating form, which is good for traveling through the fluid medium. On the other hand, the force form is the acting form, which is good for exerting force on a plane. In the flowing fluid medium, stress travels in the form of momentum flux towards the receiving plane. When the stress reaches the plane, it will transform into the force form in order to exert force on the plane. The resultant force can be in any direction, shear or normal, depending on the momentum source. Only the force vectors are shown on this stress cube diagram, not the flux vectors. To complete the picture, we need to mark the corresponding momentum flux vector for each force vector on this stress cube diagram. Remember, the flux vector has the same magnitude with the force vector, but the different direction. Instead of using two individual tags, we can use a single tag to label the flux force pair. The done thing is to concatenate the flux unit vector and the force unit vector in this prescribed order. As for the magnitude, we change the notation from single subscript to double subscript. by adding the momentum flux direction to the force direction. Continue our labeling using this protocol. You can see each stress component is associated with a unit diet. Compared to the stress tensor diagram of solid mechanics, the stress tensor diagram of fluid mechanics looks a bit complicated. Let's see how we can simplify it. We can see that the flux vectors and the unit diet text do not need to be explicitly stated. This is because the momentum flux vectors are always perpendicular to the plane, while the unit diet text always follow the subscripts of the magnitudes, sigma ij's. Therefore, the momentum flux arrows could be omitted, so could the unit diet text. Bear in mind that these omissions are aimed at simplifying the labeling. It does not change the fact that momentum flux exists and the fact that the stresses are dietic quantities. The three stresses shown on each surface are actually the decomposition of the total stresses on each surface at point P, point Q, and point R. Because the cube has a finite size, the component stresses on each surface may vary from place to place on the surface. However, if the cube is reduced to a very small, infinitesimally small volume, each surface will be no wider than a point, and there will be no room for the stresses to vary across. In such case, we will have a total of only 9 stresses, 3 on each surface. Finally, we have expressed the stress tensor in diagram form. The other 3 common expressions of the stress tensor are the matrix form, the sum form, and the word form. The stress tensor is crucial in the study of fluid mechanics. It has 9 components. Each of them is a tensor. These components constitute the basic term to express the total stress and forces in a fluid under various flow conditions. That's pretty much everything about the diagramming of the stress tensor, but it's not enough if your goal is to solve complex and open-ended problems. For that, we need intuition. Where to get the intuition? Yes, by looking at simple problems deeply and from various angles. For today's topic of the diagramming of the stress tensor, it's good enough if you can find the relationship between the matrix form and the diagram form of the stress tensor. Let's do it now by checking out the relationship and the connections between the diagram form and the matrix form of the stress tensor. Let's look at the arrangement of these 9 stresses in the stress tensor matrix. X-plane stresses are placed on the first row, followed by Y-plane stresses and C-plane stresses. So the rows represent the planes of the stress. What about the column? The first column holds the stresses acting in the X direction. The second column, stresses acting in the Y direction. And the third column, stresses acting in the Z direction. If each stress element is indicated by sigma ij, I denotes the plane orientation and J denotes the force direction. Also, when I equals J, it is a normal stress. The 3 main diagonal elements are normal stresses. When I is not equal to J, it is a shear stress. The 6 non-diagonal elements are shear stresses. That's all from me for this episode. I hope you are now visually enlightened about the stress tensor. If this video is helpful for you, you can show your support by hitting the like and share buttons. Consider subscribe also if you want more intuitive educational videos like this from my channel. Before rewatching this video, you might want to watch this video to gain some very fundamental basics on stress tensor. I'm Kyle Tan. See you in my next video.